And autofocus is on. All right. So this first question is just kind of where we ended on Tuesday. So a teacher records grades. Again, almost the same question that we kind of used all Tuesday when we talked about graphs. We mainly talked about those letter grades. This, you'll note, is different. And the fundamental difference is that these are not letter grades. These are numerical grades. These are a 20-point quiz for 30 students. And these are the grades. So it's out of 20 points. So you'll notice the highest that you get is 20. And it seems that you had three kids who had no idea what was going on. So everyone else was decent. Maybe this 12 is questionable, but everyone else is okay. And what we want to do is we want to make a histogram for the grades. And a histogram here, so remember yesterday we had, where are my notes? I always staple them and throw them on the floor. Yeah, just a second. Yesterday we had bar graphs. I'm trying to find a picture. Here. We talked about bar graphs. We talked about pie graphs, and we talked about line charts and histograms, and that's it. So bar graphs are great when you have categorical data. So data that fits into a category or a bin it's generally qualitative. So it's not numerical. So A, B, C, D, and F, they're not numbers. As we are, like our condition for qualitative versus quantitative was if you could average them. And you, strictly speaking, as letter grades, you cannot really average these. So they're qualitative or categorical. If you look I'm sorry about the bird clock again. If you look at some books, you'll notice they'll call them bins. You put them in bins, and it's the same thing as just categories. Like you think of dump trucks, you're sorting garbage, you put it in one bin or the other bin. So these are great for this. But our data is no longer letter grades, it's number grades. And so theoretically, we could do the same thing that we did for that, where we could, it's not great, but you could consider each grade to be a category or bin, but it's not a good idea. A better way is to consider it as quantitative data or number, kind of going numerically, right? Like they're numbers, you can average these. You could add them all together, divide by 30, and you'd have something. So for that kind of thing, we usually want a histogram. And so remember a histogram, let me pull up a picture from that. A histogram, instead of just having A, B, C, D, whatever, we had, or not E, F, we had the actual ranges, all right? So that's what we'll do for this one. Just note, you could theoretically do it the other way, it's just kind of awkward. So let's do it. Oh, the one thing we should do first is we should also tally up the grades, right? So let's see, how should we do this? Let me get a new sheet of paper. All right, so we'll tally them up and then we will make our chart. And so to tally them up, I'm just gonna go through and record. So I have, let's see, I think I have 20 to 16, 20, 19, 18, 17, 16. So let's see, I have 1, 2, 3, 4, I have 4 19s apparently. Oh, and I have 20s too, oops. I have 1, 2, 3, 4, 5 20s. All right, 18s, 1, 2, 3, 4, 5, 6, 7, 8.
Matt, there are 6 20s.
Oh my God. 6, thank you. And then I think there are 8 18s. If in the end we get the wrong number, we'll just fudge it. It's okay. No, it'll be fine. 17, I got this guy there. My tickings aren't really working for me. 1, 2, 3, 4, 17s, 16s. I don't know why there's 30 of these. 1. Is that it? Oh, 2 16s. And then we got some 15s, some errant 15s. Just one. Oh, two 15s. And then what else do we have? Oh, that was the other 20 you mentioned. Thank you. I think we have almost everything. Let's double check. Oh, we got a 12, the ugly 12, and then the bad grades. All right, so we got a 12, I have one of those, and then I have a 5, I have one of those, and I have 2 zeros. Right? So that's like a generally a kind of a typical grade, like a scale actually. Like I mean, you would expect to have more down here, like between 12 and 0, but a lot, what this would imply, like if you're trying to understand why these grades were accumulated this way, is it would imply that like this test was almost too easy. Um, because you have all these grades up in the higher ranges and you have almost no one in the bottom. So what happens is that most of the kids or the students know what's going on, and then you got like these 3 or 4 guys down here who have no idea what's going on, and so they just fail because they don't follow along in class. And these guys are good because they follow along at a minimal level. But yeah, so and if it was a harder test, you'd find kind of it's like a bell curve. You'd find more of that if you've ever taken a statistics course like in high school or something. But all right, now we can do the histogram. So let's get some my paper. So I'll just lay it out like this, like that. And label as much as you like. What I'll do is I'll go from 0 to 20. So 0 is at the origin, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 16, 17, 18, 19, 20. Far too many. All right. And then you put bars at each. Maybe I'll need one more actually. So that's okay. I'll do it like that. So 0, there's 2 zeros. So, and I go up to what, 8? 1, 2, 3, 4, 5, 6, 7, 8. All right. So that's 8. And this is hopefully 20. Yeah, we'll see. All right. And yeah, so if we're doing a line chart, you could just put a plot and see, but we're doing a bar chart. So what I want to do is you would kind of make it look nice. So I'll put my 0 bar. I guess I'll put my 0 bar right there. So this would be my 0 bar. This is my 1 bar, 2 bar, 3 bar. Let's see, that should work. So 0's here. And again, it's basically the same thing as if you were doing a bar graph, but the difference is we didn't leave out any of the grades. A bar graph, you'd generally want to put them all close together. So what we'll have here is we have 2 zeros. We have 1, 5. So 0, 1, 2, 3, 4, 5. We got one of those guys. And then we have 1, 12. 6, 7, 8, 9, 10, 11, 12. All right. And so it's kind of interesting. You'll see in the end. So we have 2 15s. So that's 12, 13, 14, 15. We have 2 16s. We have 4 17s. So 1, 2, 3, 4. Kind of estimating. There you go. It's not going to be pretty. We have 8 18s. So it goes all the way to the top. I'll need a few more bars. We have 4 19s. And we have 6 20s. There we go. So zeros over here, and there's kind of each little bubbles of 1 to 0. Or yeah, each little bubbles little one, blocks is a 1. But what's interesting about the histogram in comparison, and again, you can label, so 0. It's okay. I'll do 1, 2, 3, and so on. You can just keep going. But what's interesting is, but the histogram is interesting because it shows you the distribution, right? So you can really see that you have this kind of clump over here, and you hardly have anything in the middle. If you wanted to make a bar graph, as I said, what you usually do is you condense it, and so you just have the categories. You would just have 0. You'd just have 5, 12, and so on, all clumped together, and you really couldn't tell. But on a histogram, since we have all these spaces that we don't really use, you can see what's happening with the distribution. It's a little funky. All right, but yeah, and there's really no right or wrong way to do any present graph or data. It's just better ways. All right. So that's my example that we kind of did on Tuesday, but now we can move on. Today we're talking about correlation and causation. We'll put that there. And so it's another, like, again, statistics is a whole course. It's like, I think it's a year-long course, or it could be. And so it's a major too. So it's quite involved. And so we're talking about just a teeny bit in this class, but this is really hard, correlation and causation, like understanding when something actually causes something else is difficult. But in general, a correlation exists when you have two variables, and they can be anything. And a change in one results in a change in the other. So, I have a bunch of examples here, but they can be any variables you want, any topic that you could possibly study that are linked in some way that you say there's a correlation. So, for instance, height and weight. What could be a correlation between height and weight? So like, like if you're very tall, generally speaking, you're not super thin, or like not thin, I guess, but if you're tall, you weigh more because there's physically more of you. Like you're taller. So taller. So maybe I'll say height goes up, weight goes up. And the thing to note is that these are they're trends. They're not, it's not explicitly one to the other. It's kind of just as one goes up, you generally see the other go up. You don't often see really tall people who weigh like 60 pounds. I mean, you do, they probably exist, but it's not a general thing. Same thing, BMI and cancer. Again, you have very healthy people. You have people who have no health issues who weighs whatever, and then you have people who have BMI that their doctor would tell them to have that get sick a lot. So there are exceptions to these rules, but they're just general. So BMI is your body mass index. I think that's what it is. Basically, it's like your weight compared to your height. And there's whole charts that detail like if your height is this, then your weight should be in this range for you to be like healthy. And so the higher your BMI, generally the more incidence of cancer. Right. And I'm sure the details are very specific. There are a lot of details for all these, right? Like, I mean, this one's pretty simple, but for this one, you might see certain kinds of cancer pop up with people with higher BMI. And BMI is just a very general gauge to begin with. So you might have exceptions where you could be, maybe your BMI is really high, but for some reason you have other things going on. I don't know. But so there are a lot of exceptions. Elevation climbed and temperature. I don't know if you've ever climbed really high things, but like if you've ever gone out to like the Rockies or like the Washington State or something and gone to really high mountains like 10,000 14,000 feet, you'll notice it's colder. And it's just a general thing. Even if you go to the top of these hills, like if you drive up Chapel Hill on a day when it's like 34 in the valley, it might be 32 on the top of the hill, and there might still be more snow. So even these small, like 700, 800, 600 foot verticals, you do have this trend too, where the elevation goes up, temperature goes down. Right, so the higher you go, the lower the temperature, generally. I don't know if there are many exceptions to that though. Height and shoe size, this one's kind of like the first one, but if you'll find people who are taller have bigger feet, I think it's just a practical matter of support. Like if they didn't have big feet, they would fall over. So it's like evolution has been like, oh, you need big feet because you're tall. So height up, shoe size up. Right. So general trends, right? And the one way we'll often look for correlations is through something called the scatter plot. Scatter plot. It's very aptly named. It's just a bunch of dots on a chart. Right? And again, it represents two values or two variables. I mean. Oh, and so let's do one. Let me get some data. I have this old textbook that has some good examples. So let's see. Maybe actually, can I do this? Let's see if I can do this. Move this over here, make things fit without falling off my desk. Alrighty, so we have this chart here. And so what we have is we have states we have their average teacher salary, and we have pupil expenditure in dollars. All right. So what we're going to do is we're just going to plot them. And so before we get into that, I guess I should show you an example. And there's more examples in our textbook, but this one has nice pictures. So let me find here. So like, here's an example of a scatter plot. Can you use that work? So on the one axis, we have one variable, and on the other axis, we'll have another variable. So in this case, this is a graph. This is a scatter plot of U.S. unemployment and inflation. So you'll find the inflation rate, and you'll find the unemployment rate, and you can look for trends and patterns. In this case, it's just a bunch of dots. So in this case, you wouldn't. There's really no correlation, right? Like as the unemployment rate goes up, you don't see the inflation rate doing much of anything, and as the inflation rate goes up, the unemployment rate is kind of just still very chill. Let me show you another example that I had too. I guess we should do this before I do an example myself. So sorry. Here. So here's another one. This one's more interesting. Well, or more interesting, I guess. Fitting. So in this graph, we have heart disease. So this is deaths per 100,000 people. Sorry. And on this axis, we have wine consumed. So this is in liters of wine per person per year, right? And you might drink more wine than this a year. You might drink less wine than this a year. I don't know. Anyway, I might have a problem. So the more wine you drink, right, you can kind of see that as wine is consumed, the heart disease deaths go down. So, and again, we're not talking about we're not talking about things causing it. Like just because this happens doesn't necessarily mean that drinking more wine causes you to be healthier, heart healthy. It's just saying there might be there might be a relationship between them that we can look further into. But anyway, so yeah, so you have this dot, and what you do is you say, oh, I can draw this line through them, right? And it kind of fits that trend. Like there are some off, right? Like we were talking about with the height and the weight, there are going to be exceptions to most rules. So there are some that aren't quite on my line, but it doesn't really matter. We're talking about general, in a kind of generality, all right? And there's another one too I got. So this is, move my camera up a little. This is Old Faithful. Old Faithful is a geyser in Yellowstone, if you are unaware. And geysers, again, if you're unaware, they're like pockets of water that magma causes to boil. And eventually the pressure from the boiling and the magma is such that it blows through the top, the water. The magma doesn't go anywhere, to my knowledge. Anyway, so on some regularity, you have just explosions of water out of the ground, and it's like really hot water because it's steam and stuff. But what some of them are so regular. This one is famous because it's called Old Faithful. It's faithful, like it keeps coming back at the same time. But there is some variation, right? So this bottom axis is the eruption duration. So this is the time between eruptions. So maybe it erupts 3 minutes after the previous one. Oh no, sorry, this is the eruption duration. This is how long the eruption is. I'm sorry about that. I'm not reading carefully. This is how long it is. So it erupts for 3 minutes. It erupts for 4 minutes, and so on and so forth. And then this one over here, this is the waiting time. This is the difference between the eruptions. That's what I mean. So this is how long between each eruption it is. So it's gonna be 50 minutes, 60 minutes, and so on. And there's actually an app that you can download from the Park Service that will tell you. It has not just Old Faithful, it has all the different geysers in Yellowstone, and I'm assuming the surrounding areas. And it will tell you when the estimated next eruption is. It's kind of cool. If you ever get a chance to go to Wyoming, you can use it, and you can go around and see the different eruptions at the individual geysers and stuff. But in any case, this is another example of one where there's a general trend, right? Like if you took your pen and you laid it on the graph, on the scatter plot, you can kind of see that generally you have this upward relationship. So basically what that means is that as the eruption durations increase, you generally need to wait longer between eruptions. And that makes perfect sense, right? Because basically what's happening is that the pressure and the, I don't know, the water, the pressure is building up in this like underground cavern or whatever. It probably has a name. I'm not a geology person. This underground area, And the longer the pressure builds, what that essentially means is that it's building more and more. And so as it builds more and more, it's going to erupt for longer and longer. That's essentially what it means. And then the same for the lower. If you wait, if it doesn't build up for a long period of time, it won't erupt for a long period of time because the pressure in water, maybe, I'm not sure, will be less, right? And so you have this kind of positive trend. So we call this a positive correlation. The other one, the wine, we call it a negative correlation, right? Kind of for obvious reasons, like their line is going down. If you were to think of it being a line, it goes down, negative slope. All right. Anyway, so let's try that example I have. There we go. All right, so let's try it. So what I'm going to do to make a scatter plot, all you do is you first make axes that fit your data, and it doesn't really matter which you put where. It should kind of work either way. So let's see if I can. Maybe I'll do this. So we'll make a little thing like this. I should use a pencil too. I always use pencils when doing graphs. If I have one, I don't think I do. It's okay. So, and then you just figure out what your scale should be, right? So you have, maybe I'll put the salary for teachers on the X, where the X-axis would be. So this is teacher salary. And maybe I'll put the pupil, per pupil expenditure on the vertical. I'm gonna put up here. Pupil expenditure, all right? But now we got to figure out a good scale, like a good, good, how our ticks going to be, that kind of thing. So the salary for the teachers, the lowest it goes is Utah and Arizona, looks like 45,000. And we're going to be a very rough guess, or rough plotting. All right, so 45,000, and the highest it goes is Massachusetts at 75-ish. So 45 to 75. So maybe we'll do, so put 45 down here. 45K, and then I need to go up to 75, so 30. So let's see if I can fit 30 ticks in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. That was beautiful. All right, 75. Okay, so that's 75K. All right, and then for the per pupil expenditure, we have the lowest we go is, looks like around 7,000, and the highest we go is around 20,000. So 7 to 20. We'll just do the same kind of thing. I'll put 7 over here. 7,000. I'm approximating the numbers, and then we go to 20. So we can do little bigger dashes here. 1, 2. Oh, that was terrible. I'll put 2 there. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, perfect. So then again, this would be 20,000. Right? Oh, shoot, I did it the wrong way. This is per pupil. And this is teacher. I'm so sorry. I did say I should have used a pencil. All right, anyway, now we can plot. So what I'll do is I will just start with Alabama. And so at 48,000, again, I'll do it really rough. 48,000, they're at 9,000. So I go to 48. So 1, 2, 3, which is right there. And I go over, I said 9. So 7, 8, 9. And I'll put a little dot. All right. And we just keep going. So Alaska's 66 and 20. So 66. Oh, goodness, I should have labeled some of these into my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll put 10 there, or 55. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Put 65. There we go. All right, that's a little better. 66 and then 20. So right about there and over to 20. All right, and you just keep doing this. So 45, 7. So 45, 7, they're around the same place. Oh, 7, sorry. 45, 7 down here. There. Connecticut, 71, 17. So up 71, and then 19, 18, 17. So it's around there. Right. And what you're kind of seeing is you're kind of already seeing a positive trend, right? Like you lay your pencil down and like if you were to put a line that kind of best fit these dots, you're already, if we have 4 dots, you're already seeing kind of a good trend. But you can keep going. I'll just do a few more. Massachusetts 75, 16, 75, and then 16 is gonna be like here. This one's a little off more, but it's still in the good trend. North Dakota 50, 85. So 50 is like around here. And then 85 is around here. Okay. But yeah, so you kind of see, right? So you have this kind of like positive trend. And so this is a scatter plot. For a scatter plot is just a bunch of dots. You'll often see like people drawing lines through them or trying to find lines that best fit. That's not really part of the scatter plot. That's just you trying to find a trend or trying to find some kind of relationship that fits the data. But yeah, so we're kind of just going up. And you could keep plotting if you wanted to. I think you probably get the idea at this point. But yeah, so you label the axes, you find a good scale, and then you just start plotting points, and you should see a trend. So this trend, what that would imply, if this was it, so like something like that, what that means is that as per pupil expenditures go up, teacher salary also goes up, all right? But those two probably aren't related. I mean, they are related, but what's probably happening does anyone have any idea why they're probably related? What's happening? Why teacher salaries goes up with per pupil spending? So like, you probably just have wealthier school districts, and so these wealthier school districts have more money to spend per pupil, and they also have more money to spend on their teacher salaries. Whereas when you have poor districts or less funded districts, you have less money to spend in general. So these two are probably linked just as a function that they come from the same budget. That's all. There's not necessarily a relationship between the two. All right, let's do one more. Do I have one with a negative trend? Let's try this one. Yeah, let's try one more. I don't know. This one's good, actually. Down here. So this one is a list of countries, right? Literacy rates and infant mortality rates. So infant mortality rates, how many infants die per birth, basically. This is per 1,000 births, but it's just relating how many die per each born. So we can try this one too. So we have a bunch of countries again. Then we had a bunch of states earlier. We have a bunch of countries now. The literacy rates are percentages ranging from 39 in Afghanistan, which is depressingly low, up to 99 in the United States. You wouldn't know it. And then infant mortality rate per 1,000 births, they range as low as three in Austria and Germany, and as high, depressingly, as 66 in Afghanistan. So yeah, so what we're going to do is plot those two. So again, I'll draw my axes. It does again, and it also doesn't matter which order you have. You can put either or. You should see a pattern regardless. So I'll put literacy rate down here, and I'll try to do it this time in the right spot. And then I'll put infant mortality rate on the vertical. Infant mortality rate. There. And now I just need to label everything, or number it, I guess. So 38 to 100. Ugh, I don't know. I'll do, I'll put 38 here. And I guess I'll just go by tens. So this is about 40. We'll say it's 40. So 50, 60, 70, 80, 90, 100. All right, so I'll scribble that out and say 40. All right, so that's as a percent. And then the infant mortality rate, as I said, we move from 3 to 66. So I don't know. We'll start down here. We'll say it's 0 and 60. We'll do by tens as well. Make our life simple. 10, 20, 30, 40, 50, and 60. Oh, a little more, 70. There we go. All right, and always plot. So Afghanistan, literacy rate's 38, infant mortality is 66. So 38 and then 66, goodness gracious. All right. 98 and 3. So 98's over here and 3 is down there. And 2 dots, and you can already probably guess the pattern, right? Like you have one there. If you connect them, you can probably guess, and your intuition might tell you that the pattern is going to be negatively, they're going to be negative correlation, because as literacy rate increases, you'd expect that the infant mortality rate would go down, because presumably if you have a country with a high literacy rate, it's more developed or has more resources, and they're able to have better medical infrastructure and stuff like that. So to reduce the infant mortality rate. We can keep going. We'll do a few more. 88 and 54. So that's, see, this is kind of surprising too. 86% literacy rate in Burundi, but they have a 54 infant mortality rate. So that's kind of odd. It's going to be an outlier. 86, 54. 86, 54. All right. So an outlier is just anything that doesn't fit your trend. So if we anticipate this being our trend, Burundi is an outlier. I don't know what's happening in Burundi. Colombia is 95-14, better than Burundi. 95-14. Ethiopia, 49-41. So it's kind of right smack dab in the middle. 49-41. Germany, 99-3. 99-3. How do you have such a high literacy rate? It's crazy. Right, 99-3. And then let's just, I guess we can finish. We're almost done. Liberia, 48-53. 48-53. Again, I'm just very, very estimating. New Zealand, 99-5. Again, I'm kind of running out of space for the dots. I'm just kind of putting them right next to each other. Turkey, 95-12. That's 95-12. A little higher than you'd expect, but I guess it's Turkey. And then United States, 99-6. 99-6, somewhere there. All right, so I guess they're kind of clumpy at the bottom, but you can kind of see the trend. And if with your, if you had, on this on your own, you could do it as nice as you wanted. But you can kind of see the trend, right? And I don't know, Burundi is weird. Like, I don't know why Burundi's an outlier. All right, but it's okay. As I said before, there's going to be things that don't fit your trend. That's always going to be. Even up here at the top, there's some, like this guy here, he should be a little higher to fit with his friends. And these guys here are a little high too. So even the United States is a little high, having 99% literacy rate, but it's 6%. I don't know why New Zealand's also on the higher end, 5 and 6. We should probably try to be lower. But there you go. So then you can kind of draw the same. If you wanted to, you could draw the same kind of line. Trying to find the line of best fit. Any questions with this so far? So scatter plots. All right, so let me move this massive book. The book's heavy. Alrighty, back to my notes. All right. Oh, we already talked about this. So both variables increase and decrease together. So it was a positive correlation. All right, so let's see. So this one, as literacy rate increased, infant mortality rate decreased. The countries with the highest literacy rate had the lowest infant mortality rate. So since they're opposites, as one goes up, the other goes down, it's a not positive, it's negative. So two variables change in opposite directions. All right. The positive one would be that first one we did. Where'd it go? Apparently I lost. Oh, it fell off my table, just a second. This one. So this one has a positive correlation because as per pupil spending goes up, teacher salary also goes up. So they both go up. And it doesn't even matter that they're going up. They could both go down. If they both went down at the same time, then it would also be positive. It's a matter of if they're going in the same direction, not necessarily the positive direction. Right? So negative, positive. And then if there's no apparent relationship, there's just no correlation. Right? They seemingly are unrelated. Like the that one, I was drawn on the picture. So like, and we'll say this correlation is stronger. We put this in. It's stronger if more variables fit the pattern. So less of those dots like Burundi. right? Unless outliers that are kind of off your line. So for instance, if I had this one here, right, just a bunch of dots on a page. um, there's no relation, there's no correlation, right? There's just a bunch of dots. If I took my pen and tried to position it so that it kind of hit some of them, it wouldn't work. So there's no correlation. Right, and so like if I had something like this, like we had in the teacher, right, something like this, right, that would be positive correlation. In this case, as this one goes up, this one also goes up. Okay, positive. And then again, like the Burundi one, this one would be negative. So something like this. That would be negative. And you don't really need to memorize anything, right? But because the positive one will correspond to like a positively sloped line, the negative one will correspond to a negatively sloped line. Yeah, right. So I think the examples are kind of, the pictures I think work better than some of the definitions. But fine. So if you have in a situation like this, like teacher salary versus per pupil expenditures, then you might say, oh, if we pay our students more, then the teacher salaries will go up. But that's, as I said, that's not necessarily true. There's not a relationship between them as their own variables. Like this variable going up does not necessarily imply that the teacher salaries will go up. And so there's different things at play, right? And so in this case, we would say there's an underlying variable. The underlying variable is the school's budget. And so that would be underlying cause for this causes of correlation. Another cause of correlation might just be pure coincidence. So that one is I think people often forget that that's a possibility. So that's another possibility. So let's see, in this example I have down here at the bottom of this page, this is actually true. The result of the home game, the last home game by the Redskins correctly predicted the presidential election from 36 to 2008. Isn't that crazy? So basically what the system was that if the Redskins won, the incumbent won. If they lost, the incumbent lost. So basically their outcome was the exact same as the presidential outcome in these years, which is quite a number of times. And it's just, there's no reason that this is true. It's just coincidence. I mean, you could be a conspiracy theorist and somehow think that the Redskins, I mean, this is why conspiracy theories exist, because people don't understand that coincidence, or they don't want to think that coincidence can be a possibility for causing some correlation. Like it's wildly unlikely, right? Like, if you imagine it as a coin toss, how many elections were between 2008 and 1936, right? So you take the difference, divide by 4, one every 4 years. There were 18 elections. So if you imagine 18 coin tosses and then 18 coin tosses for the Redskins, they all have to match up 18 times in a row. Now, I don't think it's true anymore. I think this has failed. I think in the 2012 election, it didn't work. So RIP, the conspiracy theory. But it's amazing, isn't it? Because if you had 2 coins and you flip them at the same time 18 times in a row, there's almost no chance that they would line up. But this did. So just because something happened and it's a wildly impossible coincidence doesn't mean it's not a coincidence. It's just kind of funny that it worked for so long. So that's an example of a coincidence. It's just, it means nothing. It means absolutely nothing. The underlying cause, if you find that there's an underlying cause to your correlation, that's good, because then you understand why the correlation exists. So that's not necessarily a bad thing that there's an underlying cause. It just means you shouldn't think that one variable doing something is going to cause the other variable to do something. You have to work on the underlying cause to cause change. And then the last possibility, which is often rare, is that it's causation. So one thing causing another, right? So, and this is what you would want to show, presumably. So if you're doing a study and you get a bunch of data and you plot it and you show there's a correlation, it doesn't necessarily mean that there's a causation. Like, it just means that you've shown that the two variables are related in some way, but you haven't shown that the cause is actually what you have. It's kind of difficult to show causation in a lot of cases, I think, just because it's easy to show using statistics that things are related in some correlation, but it's difficult to show that they're causing each other. Luckily, we don't have this problem in math because everything we do is just cause, unless you're in statistics. Otherwise, in math, it's very straightforward. Everything is bam, bam, bam. There's no like, oh, it could happen. Anyway, so one more example I wanted to do was this one. So, and it's a little morbid, but it's also kind of funny. As ice cream sales goes up, drownings go up. What type of correlation is this?
Would it be like an underlying cause?
Yeah. What do you think? What's the underlying cause?
Well, ice cream sales go up, more drownings. It's probably a hot summer.
Yeah, it's just the summer. Summer is underlying cause. So there's a correlation, but they're not actually related. Like, your ice cream sales going up isn't killing children. It's just that summer is, because the more during the summer people buy ice cream and then they go in the pool more, so they drown more. But that's it. There's no actual cause. But it's very dangerous, this kind of thing, because a lot of times you'll see people say things that, you're like, oh, this is related. There's a correlation between these two variables, and it's easy to use that to argue, a million different points. But actually showing that there's a causation is different. So a lot of times people will talk about correlations when they mean a lot of times people talk about causations, or like something causing something, when they really mean that the two are correlated. So you have to be very careful. And this is kind of another thing, how it kind of plays into the statistical studies and stuff like that, because a lot of studies, or a lot of people reading studies, I guess, will kind of jump to conclusions. Or a lot of news articles that quote like studies, like you always see like different reports about how coffee or wine is going to save your life or something, but they're really just showing correlation generally. They're not actually talking about causation. So a lot of these articles will say like, oh, drinking 5 glasses of wine a week will save your life or something, but it really probably won't. It just might help because there's some correlation between the two, and they don't necessarily understand why it exists or even how it works. So there might be more factors at play that are gonna cause you issues if you're trying to, use this to save your life somehow. But yeah, any questions about any of this? All right, I just wanted to do one more thing. Cool. So the other topic, we talked a lot about graphs. We talked about causation and correlation. I just want to talk a little bit about other kinds of graphs that we haven't talked about, and I want to get some good pictures, so I have this book here. And so there's a bunch of different graphics you can look at, right? So there's a billion different variations on graphs. And so like on the final, I'm going to put some different examples of graphs, and you're going to have to kind of interpret them and read the data from them and use it. So for instance, if I had a graph like this, oops, sorry, I'm trying to get a good view of it without the glare. That's not much better. Oh, wait, there we go. That's not bad. So this graph here, trends and death rates for 4 serious diseases, right? And it gives you some ranges. And over here, we have deaths per 100,000. And we have a key. So this kind of beigey color is pneumonia. This kind of greenish color is cardiovascular. The blue is tuberculosis, and the purplish color is cancer. And so, again, there's a billion different variations on graphs like this. So just, make sure you're interpreting them. Read them carefully when you see graphs, because there's not really a way that we can go through and talk about every different kind of graph, because people present data in a ton of different ways. So on this one, You know, what you want to do is if you were asked like, you know, in 2000, you know, how many deaths per 100,000 were there from cancer, you would just see how big the purple chunk is, right? So like, you know, you go to 2000, go up, go over, a little over 200. Now, it gets a little trickier because if I wanted the green, if I wanted the deaths per 100,000 in the cardiovascular in 2000, I can't just go to the top and go over because that would also include these deaths from cancer. So when you're reading graphs, just be careful you're reading it because like here, I'd have to look up here and say, oh, in 2000 there were, you know, maybe just 600,000 or 600 deaths. But this is on top of the cancer deaths. So I subtract off the 200 I took for cancer. So I'm just talking about this distance here essentially. So it'd be 600 minus the 200. So it'd be the length, the 400 deaths per 100,000, right? Um, but yeah, so just be very careful when you're doing graphs. As I said, one of these would be on the final. It kind of looks like this one, but there's other ways you can present data as well. So like here's an example of a graph. This is just a simple bar graph, right? But you'll notice it has multiple bars and different categories for the bars. So this is math test results. Boys are blue and girls are like this red color. It's probably supposed to be pink. Um, and the mean score, you have some numbers. I don't know what they represent here. And then you have each country. All right. So, you know, if if I asked you South Korea's test results for boys, you just go to South Korea and find that one. So this was not too bad. Again, infinite variations. Another one could look like this. Sorry for the glare again. This is undergraduate budgets for full-time students, 2016 to 17. And it just breaks down different parts of budgets. So you have tuition and fees from the board, books, transportation, all that stuff. And then it gives you different campuses, right? So public 2-year, 4-year in state, out of state, private, that kind of thing. And then it breaks it down. So, you know, for public 2-year commuter, which is the cheapest you're going to get, your general costs, you know, look something like this. So 32,000, 3,200, 8,000, yada, yada. And in this graph, they're being nice because they tell you how much each chunk is worth. Exactly. But they could be not nice. And what they could do is they could just, you know, make you go down and figure out how big the chunk is. All right. So for instance, for the 8,000, this chunk is 8,000, right? But if I go over here and read down, I get like, I don't know, 12,000. So you might say 12,000, but you have to remember that there's this chunk in the beginning that's not part of the light blue. This dark chunk is tuition. This one's board. So if I have to go down to 12,000 and then go over here and figure out what this is, it's like 3,000 and take the difference. All right. So you get around 8,000 depending on how accurate you were. And that's just really it. So that's the last thing I just wanted to note. Just be very careful when talking about graphs. You know, here's a couple other kinds you'll see. So this is basically a line chart, right? But it's just got multiple line charts on top of each other. So, and they'll always give you a key. So like this one, not a high school graduate. This one's unemployment rate for individuals of certain types. So not a high school, college with a college degree. So the highest unemployment rates are among people without high school diplomas. And then as you get more and more education, your unemployment rates generally go down. Okay, so this peachy color is bachelor degree or higher, and they have the lowest unemployment rate. Again, there are exceptions, but this is just generalness. And this one over here, this is just a bar graph essentially, like we talked about with the South Korea thing, the math grades. But you got multiple bar graphs. This one's horizontal instead of vertical. Doesn't change anything. This is median annual earnings of workers, depending on the degree. So you'll see that the lowest are not a high school graduate, so they don't even have their high school degree. And then as you go up, you have some college, your pay gets a little better, your associates a little better, not by much, and then you get bachelor's and it goes up a bit, master's, doctoral degree, professional degree, and it goes up more. I think professional degree, oh yeah, MD or JD. So you know, like a doctor, you get your doctoral degree, and then you have to go to like a residency and stuff. So you have more like education on top of your doctorate degree as a doctor. So that's what the professional degree is there. But it just will get higher and higher. And then it's split between men and women. It's really surprising that women make so much less than the professional degree. It's kind of curious. But anyway, any questions? So, we talked about that. That's basically the kind of rough view of statistics we'll do. Mostly about sampling and like just kind of basics on the studies. And one of the purposes I think is useful is just to try to get you a handle on how you could read studies. So really, if you're like arguing with a friend or something and they send you a study and you're like, this is nonsense, and I'm going to tell you why. So I hope just to give you like a bit of that so that, in a practical sense, you can try to understand some statistical studies to an extent in case they do pop up at some point in your life. But any issues, questions, concerns about anything through the rest of the semester? No. All right, so that's it. That was the last of the new material. It's very exciting. On Tuesday, we will do the test. The test review. And then we'll be done. That will be it. That'll be a curtain. So if you have any questions in the meantime, again, I have to move my Zoom or my office hours tonight to Saturday night. And I'll put it on Blackboard. I'll try to have some extras on Saturday night too, because I know it's like a lot of crunch time for people. If you have questions in the meantime, though, you can still email me, obviously. But that's it. All right, so I'll see you guys on Tuesday, and we'll do the review for the test, and then I'll put the test up, and we'll be good to go. All right.
I just wanted to let you know